This is slide number 65 and I am your presenter Asloob Mudassar. Fourier plane filters. Before the advent of special light modulators or where such instruments were not available, amplitude and or phase filters were made using photosensitive material on glass substrate, which we may call photoglass. The photoglass are exposed with the desired pattern and the developed plates act as amplitude filters. The thickness of the developed emulsion, if variable, may also act as a phase object, and this phase effect can be removed by immersing the developed glass plate in a liquid gate. Phase objects are relatively difficult to make. The photoglass is exposed with the required phase pattern. The photomaterial with no exposure is removed during the developing process, and the exposed material is bleached to make the exposed material transparent. The thickness of the transparent bleached material is proportional to the time of exposure. The thickness of the transparent emulsion can be developed. The thickness of the transparent emulsion on the developed glass plate varies as a function of illumination brightness. This is how a phase object is constructed on a photoglass. The control of both amplitude and phase at a Fourier plane is done by using separate amplitude and separate phase filters placed together. This scheme works only for simple filters. These filters can control the amplitude and phase of a coherent transfer function in a given coherent processor. Amplitude and phase, that is two-in-one filters, can be realized interferometrically. An object in the transmission mode is placed in a coherent processor and its Fourier spectrum is generated at a Fourier plane. The photoglass is placed at the Fourier plane and an additional coherent beam generated from the same single source called reference beam is used to illuminate the glass plate. The two beams interfere at the Fourier plane and the glass plate is exposed with the interference pattern. The developed dried glass plate acts as a Fourier transform hologram abbreviated as FTH of the input object and was first introduced by van der Loo. Fourier transform hologram is prepared for one object and then it is used as a frequency plane filter for another object placed in the coherent processor. Fourier transform hologram is placed at the same location in the Fourier plane identical to its location during the development process. Fourier transform holograms are sometimes developed in situ without disturbing the position and orientation of the exposed glass plate and in the environment of constant temperature to eliminate the effect of any variation in interference pattern. A variety of schemes now exist for the realization of van der Loo filters, and three of them with better citations are given in the next figure, are given in the figures on the next slide. For example, this is setup 1 for generation of van der Loo filter. Look that a point source exists at the front focal plane of the lens L1. It means that a spherically diverging wavefront is incident on the lens L1. Since the point source is located at a distance f in front of the lens, which is the focal length of the lens L1, so the lens L1 will generate plane waves on the right side of it. A part of the plane wave illuminates the object just placed after the lens L1. So the light will pass through the object and is received at the lens L2. The object is also located at the front focal plane of the lens L2. And the L2 will generate the Fourier transform of this object at its back focal plane, which we refer to as the Fourier plane. Okay, then another part of the beam after the lens L1, which is also a plane wave, illuminates or incident on the prism. The prism diverts the parallel beam on the Fourier plane. So there are, which we also call the reference beam. So the beam from the lens L2 at the Fourier plane is may be called the Fourier transform beam, or may be called the object beam, and the beam from the prism at the Fourier plane may be referred to as the reference beam. These two beams interfere at the Fourier plane, and so if you place a photo glass over here and expose it, then you know that after then it means that you are recording the amplitude at the Fourier plane. So you need to develop the photosensitive or photoglass material and then dry it, and then that will act as a Fourier transform hologram. And then you know that the Waterloo filter is constructed. So this was setup 1. To optimize the space, I have placed the setup 3 over here, but let's go first to the setup 2. So the setup 2 for generation of a Waterloo filter. This is the modified Mach-Zehnder interferometer. Look at the point source is also located at the front focal plane of the lens L1. So L1 generates plane waves. So the plane waves incident on the beam splitter 1. A part of the plane wave moves towards the mirror M1, and the other part from the beam splitter moves towards the mirror M2. So the beam from the mirror M2, which is also a plane wave, illuminates the object. The object is placed at the front focal plane of the lens L2. So the L2 will generate the Fourier transform of this object at its back focal plane, that is at the Fourier plane. Now another beam, a plane beam from the mirror M2 is incident on the beam splitter 2 and is directed towards the Fourier plane. So the two beams, that is the beam from the lens L2 and the beam from the beam splitter 2, from the mirror 2, and then the beam splitter 2, and then the Fourier plane. So these two beams will interfere together and will form the Waterloo filter, Waterloo filter if you place a photosensitive material over here, for example photoglass, and expose the photoglass material. So the beam from the mirror M2 may be referred to as the reference beam, and the beam from the lens L2 may be referred to as the Fourier transform beam or the object beam. So these two beams interfere at the Fourier plane, and you see that if you place a photosensitive material or a photoglass material over here and expose it, then of course the Waterloo filter is constructed, but you need to develop the exposed photoglass plate and then dry it, and then that will act as a Fourier transform hologram. So now let's move to the setup number 3. Setup 3 for the generation of a Waterloo filter. This is actually modified Rayleigh interferometer. Now again you see that the point source is located at the front focal plane of the lens L1, and the lens L1 generates plane wave after it. A part of the plane wave illuminates the object, and the object is located in this case at a distance 2f from the lens L1. So this object, the light will pass through the object and will be received at the lens L2. The lens L2, the object is placed at the front focal plane of the lens L2. The lens L2 will generate the Fourier transform of this object at its back focal plane, which we have labeled as the Fourier plane. But you know that this object is not located or is not centered at the optical axis of the lens L2, but it is deviated from the optical center, or it is away from the optical center. That's why the Fourier transform beam after the lens L2 is actually not going straight, but it is also inclined due to the off location of the object plane from the optic axis. Now the plane wave, the part of the plane wave from the lens L1 illuminates or incident on the lens L1. Lens L3. The lens L3 now generates or focuses that one to a point source at the location where the object was placed. So the point source generated by the lens L3 and the object, they were located at the same plane. So the light from the point source will now be received at the lens L2. And the lens L2 will then convert the diverging wavefront incident on the lens L2 from the point source. The lens will generate the plane wave, but you know that this plane wave is also directed, not going to the straight, but it's also directed or bent towards the Fourier transform plane. and the bending of this light is also due to the fact that the point source is not located at the optical position or at the optical axis of the lens L2, but it is located away from the optical center, and that's why the light is deviated to or is inclined at some angle, and of course incident on the Fourier plane. So these two beam, that is the beam from the lens L2 via the point source, may be referred to as the reference beam, and the beam from the lens L2 through the object after passing received from the object and then focused at the Fourier plane may be referred to as the object beam or the Fourier transform beam. So these two beams will interfere together and will form a Fourier Vanderloo filter. So you see that we have given the descriptions of setup 1, setup 3, and of course setup 2 over here. Now we compare the features or the properties of these setups. The experimental setups in these figures are self-explanatory. In these setups, the lens L1 is used to generate a collimated beam because the point source exists at its focal plane. Following are the common characteristics of these setups. Number 1. Object transparencies are illuminated by plane wave fronts. Number 2. L2 acts as a Fourier transforming lens with the objects located at the front focal plane and their Fourier transforms are at the back focal plane. Number 3. Collimated plane wave fronts are added at the Fourier plane in the setup 1 using a prism, in the setup 2 using Maxender interferometer type arrangement, and in the setup 3 using Rayleigh interferometer type arrangement. Number 4. Interference occurs at the Fourier plane between the object Fourier spectrum and the mutually coherent plane wave fronts and is recorded on the photographic plate. Number 5. The Fourier transform FTH, the Fourier transform hologram of the given input object of the given input signal or object is thus created after the developing and the fixing process and is placed back at the original position where it was first exposed. The Fourier transform hologram of the given object thus act as amplitude and phase filter for another object placed in the coherent processor. Such Vanderloo filters have great applications in signal processing and pattern recognition domains. Next step is to write down the common mathematics for the three processors. At the frequency plane, two optical signals contribute. One is the Fourier spectrum of the input object and the second one is the plane wave inclined at an angle theta with the optical axis of the collimated beam. The reference beam reaching the Fourier plane in setup 2 makes an angle equal to 0, and this angle can be changed to a desired value by tilting the beam splitter 2. The Fourier transforming lens L2 acts in identically the same way for the processors shown in setups 1 and 2 and generates the Fourier spectrum at its back focal plane without any additional phase factor, whereas the object in setup 3 will have its Fourier transform multiplied by an additional phase factor which involves the shift of the object center with respect to the lens center. The Fourier shift theorem will be applicable in this case. Let's assume that x and y are the coordinates at the Fourier plane. Zeta and eta are the coordinates at the object plane. The object amplitude transmittance is represented by O at the coordinates zeta and eta under plane wave fronts illumination. A0 is the amplitude of the plane wave fronts generated by the collimating lens L1. The tilted plane wave at the Fourier plane makes an angle theta with the y-axis and that the object is shifted to the position AB on the object plane and that the object is located at a distance d is equal to f in front of the lens L2. Then the coherent intensity recorded at the Fourier plane is given by the following expression. So look at the expression number 13 that we have obtained for the intensity expression at the xy coordinates. So I as a function of xy coordinates is equal to the absolute square of the sum of two beams. One is the reference beam, so A0 e to the power minus iota k sine theta multiplied by y at the exponent is actually a plane wave which is inclined at an angle theta with respect to the y plane and is focused at the and this is a plane wave at the Fourier transform plane. So this is what the first beam we have written, that is A0 e to the power minus iota k sine theta into y. This is the plane wave. inclined at an angle theta. Okay, now the object beam is this one, which is e to the power iota kf. So this is actually the beam generated after passing through the object and is focused by the lens L2, forming a Fourier transform forming the Fourier transform at the Fourier transform plane. So we have some constant terms over here, which is e to the power iota kf over iota lambda f, and then the exponent term or the quadratic phase term associated with the image plane, which is e to the power iota k over 2f and multiplied by 1 minus d over f into x square plus y square within the parentheses. And then we have the Fourier transform of the object beam, that is the beam passing through the object. So the amplitude of the plane wave is a0, which illuminates the object, and the object over there is shifted at the coordinates a and b with respect to the center of the lens. So we have O as with the coordinates zeta minus a comma eta minus b. So you see that then we have taken the factor a, which is common in both terms. We have taken that one outside the absolute square bracket, and then we have the rest of the terms over here. But here we are going to introduce the Fourier transform of this quantity in the second step, which is capital O as a function of fx comma fy. So fx and fy are the Fourier frequencies related to the zeta and eta coordinates. So we have the spectrum of the object, and then you know that we have multiplied it with e to the power minus iota 2 pi. Within the parenthesis we have fx into a plus fy into b plus 1 over 4. So you see that this bracket is actually this small, you know that this exponential factor is because of the shifting theorem, because we have applied the shift theorem over here, because the shift in the phase will involve the coordinate a and b as given in step number 2 of the equation, step number 1 of the equation number 13. So we have simplified version of the equation number 13. What about the constant term over here? Let me explain in the text. Where capital O of x comma y is the Fourier transform of the object O as a function of zeta and eta, and this operator, which is the Fourier operator, the constant phase factor e to the power iota kf is physically not important and has been omitted, and the quadratic phase factor e to the power iota k over 2f. Within the parentheses we have 1 minus u over f, and the quadratic phase term also involves x square plus y square was cancelled out as the object is located at the front focal plane of the Fourier transforming lens L2, for which d is equal to f. So you see that putting d is equal to f, this phase factor will be cancelled out. In writing equation number 13, we have made use of shift theorem. The Fourier domain coordinate as a function of Fourier domain coordinates fx comma fy are related to their space domain counterparts through the relationships, that is fx is equal to x over lambda f and fy is equal to y over lambda f. We have transformed 1 over iota as given by minus iota is equal to e to the power minus iota pi by 2 is equal to e to the power minus iota 2 pi into 1 over 4. So that's why you can see that the factor 1 over 4 is because of this iota. Next we make the substitution O as a function of f comma y into e to the power minus iota 2 pi. Within the parentheses we have fx into a plus fy into b plus 1 over 4, and we are replacing this term as O prime as a function of fx comma fy. The equation 13 now transformed as given below. So making this transformation and representing this whole term, that is the shifted Fourier transform with phase factor, we are replacing it with O prime as a function of fx comma fy as shown in equation number 14. So on the left hand side we have the same quantity, and you know that we have the same quantity over here from the second step of equation number 13, but we have replaced over a new thing over here, which is O prime as a function of fx comma fy. The rest of the quantities are the same. Now you see that we can expand the term within the absolute square term as this term in the parenthesis multiplied by its complex conjugate. And now you know that we are going to do the multiplication of the second steps, and then we can write down we are writing down the third steps. Again you see that since there are 2 terms in each parenthesis, though a total of 4 terms are seen in the last step of equation number 14. And you see that here we have I of x is equal to a naught square, and within the parentheses we have 1 plus e to the power minus iota k sine of theta into y over lambda f, and multiplied by o conjugate of o prime plus e to the power iota k sine of theta into y over lambda f multiplied by o prime plus 1 over lambda square and f square, and multiplied by o prime and o prime conjugate. So this is the last step of equation number 14. Now we are going to introduce some quantities over here. O prime being a complex quantity can be written as, so O prime, so you see that we can transform the fx and fy by their relationship with the space coordinates, which is fx can be replaced by fx over lambda f, and fy can be replaced by by y over lambda f. This is what we have done. So O prime can be replaced, O prime has been shown with their space variables and can be plugged in or can be set up as a of x over lambda f comma y over lambda f as the amplitude, and then the phase factor e to the power iota sine of x over lambda f comma y over lambda f. So we have represented O prime in terms of its amplitude and in terms of its phase factors. So you see that now we are representing, so substituting O prime in equation number 14 and rearranging the terms, we have obtained the first step in equation number 15, which is a naught, and within the parentheses we have 1 plus a square over lambda square f square plus 2a over lambda f multiplied by cos of k sine of theta into y plus psi. So you see that this is simple. You can this is simple calculus, and you can see this thing in any book on interference. So you see that in the second step we have written again that we have replaced k with the value 2 pi over lambda, and then we have separated out the special frequency, which is cos of 2 pi into sine theta over lambda into y plus psi. So this sine theta over lambda is actually the special frequency of the fringes. So in the rest of the quantities are more or less the same. So this is what the second step in the equation number 15. Now I of xy as given in equation number 15 can thus be recorded on the photographic plate or on a CCD camera or on the photoglass. The pattern followed by the intensity is cosinusoidal with the spatial frequency of fringes given by. So this is the spatial frequency of the fringes, which is equal to sine theta over lambda. So you see that setting the value of angle theta, you can change the spatial frequency of the fringes in equation number 15. The exposed photographic plate having exposure pattern of the form shown in equation number 15 is developed, and dry version acts as the Fourier transform Fourier plane filter. This filter can thus be used as the Fourier plane at the Fourier plane in the coherent processor where the filter was first exposed. The amplitude transmittance of the filter can thus be written in the following form using equation number 14. So you see that we are writing equation number 14 to introduce the amplitude transmittance of this object. That is the object that we have constructed, and we have developed the amplitude transmittance filter. So the amplitude transmittance filter is given by equation number 16. So we have T with a subscript A. A stands for the amplitude transmittance of the filter, and T for the transmittance. So TA stands for the amplitude transmittance as a function of xy is proportional to these quantities from the equation number 14 we have taken. A naught square plus a naught square, and over here we have O prime absolute square over lambda square plus f square. Then we have a naught square into e to the power minus iota k sine of theta into y over lambda f. Then we have O prime conjugate plus a naught square e to the power iota k sine of theta into y over lambda f multiplied by O prime. So this is equation number 16, and this is equation number 16 that we have written from number equation number 14. You can just look at that. It is very easy to write these one. For example, where we have O prime and O prime conjugate, you can write it as O prime absolute square of O prime, and similarly the rest of the quantities are very simple to write. That is what we have written over here. And the Fourier domain variables equation number 16 takes the following form. So here we are introducing actually lambda f because we are introducing k by 2 pi over lambda f, and then we are rearranging the terms so that we can introduce y over lambda f in both of the last two terms. as you can see that in the last two terms we have introduced in the exponent as y over lambda f. And you know that y over lambda f can be replaced by fy, where fy is the Fourier frequency in the y direction. So as given in equation number 17. So equation number from equation number 16 we can write equation number, the first step in equation number 17 and then the second step in number 17 very straightforwardly. The fourth term, this is the fourth term, look at this term, very special term in equation number 17. The fourth term on the right hand side in equation number 16, that is this term, contains the object spectrum O prime, which was required in the synthesis of a frequency plane filter. The frequency mask given by equation number 16 can be inserted in any of the three coherent processors 1, 2 or 3 with the reference plane wave blocked from reaching the Fourier plane and reaching the Fourier plane. Okay, so you see that the frequency mask given by equation number 16 can be inserted in any of the three coherent processors 1, 2 and 3 with the reference plane wave blocked from reaching the Fourier plane and with the extension shown in the figure below introduced with each of the processors or equivalently for filtering the applications of the setup shown can be used. So you see that this after we have blocked the plane wave reaching each of the setup in figure 1, 2 and 3 and then using the extension with this setup we can obtain useful information over here. So LT is the second Fourier transform lens. You look at this one, L4. L4 is the second Fourier transform lens when considered a part of the processor given in setups 1, 2 and 3. So you see that this is an extension that we are going to use after the Fourier plane in each of the setups schemes 1, 2 and 3. And then we are using a lens L4 that will take the Fourier transform of the Fourier transform shown at the Fourier transform plane and then the image will be formed. Okay, when the frequency plane masks are placed at the Fourier plane, the filtering effect can be seen as images on the image plane. So you see that we have the van der Rohe filter, that is the FTH, that is the Fourier transform hologram that we have placed over here, and then you know that we can place any other object in the processors 1, 2 and 3, which because we are using this as an extension to those processors, that is you have to use this one as an extension to process 1 to the scheme 2 and to the scheme 3, that is to the coherent processor 1, 2 and 3. And then you know that you can place any of the object at these processors, but you can use the same FTH, same Fourier transform hologram over here, and then you can see the effect at the image plane, that is the effect of the filtering due to this van der Rohe filter. L4 and the image plane form an extension part of the processors in setups 1, 2 or 3 to make them complete coherent processors. Consider the coherent processor shown. The frequency mask with the amplitude transmittance given by equation number 16 is placed at the Fourier plane and another object. You see that we are now talking about another object represented by O2 at the coordinates zeta and eta, or at the plane zeta and eta is placed at the object plane. Now we are using another object. The Fourier transform was constructed with the object O, but now we are placing another object O2 as a function at the zeta and eta plane. The Fourier transform of O2 as a function of zeta and eta is generated at the back focal plane where the filter given by equation number 16 is located. The filter can be used to remove or to modify the spectral contents of O2 as a function of zeta and eta. The Fourier of O2 is given below. So you see that what is happening. Actually, what is happening is that we are now with this extension at the coherent processors Now we are using, because the Fourier transform, we have placed the Fourier transform hologram over here. This Fourier transform hologram was constructed with the object O, when the object O was placed at the zeta and eta plane. Now after placing the Fourier transform Fourier transform hologram over here, that is the frequency plane filter over here. Now we are illuminating, or we are placing at any of the three coherent processors another object which we are labeling as O2. So we are placing O2 as a function of at the plane zeta and eta, and now you know that the Fourier transform of the object O2 is generated at the location where we have placed the Fourier plane over here, Fourier filter over here at the Fourier transform plane. So you see that this filter or the FTH will do some filtering to the projected Fourier transform of the object O2 over here, and then you know that the filtering effect can be seen at the image plane. So you see that in equation 18a we are now giving the Fourier transform of the object 2 as a function of when placed at the plane zeta and eta. So we have used the operator at the object O2 on the left hand side in the curly bracket, and then we have on the right hand side the Fourier plane, the Fourier transform of O2. And you know that we have some constant terms over here. We have the quadratic phase factor over here, which is related to the image plane coordinates x square and y square, and that is e to the power iota k over 2f, and within the parentheses we have 1 minus d over f, and within the parentheses we have x square plus y square, and then you know that the Fourier transform of the object O2. Because the object O2 was illuminated with the amplitude A of the coherent of the plane wave, which is A0. So A0 multiplied by O2, and you know that O2 was placed away from the optical axis and shifted from the optical axis as we have described earlier by the coordinate by the center A and B. So AB is the center of the object where the object was placed, and you know that we have O2 with the coordinates zeta minus A and comma eta minus B, and you know that its Fourier transform we have written and we have explained that one earlier. But you see that O2, small O2 will now be replaced by capital O2 as the Fourier transform, and with the Fourier frequency fx comma fy. So you see that we are replacing this whole quantity by O2 prime. So 1 over lambda f multiplied by O2 as a function of fx comma fy and e to the power minus iota 2 pi, and with this phase factor, that is fx into a plus fy into b plus 1 over 4. This whole term, the whole second term has been in equation number 18a has been replaced by O2 prime as a function of fx comma fy in equation number 18a, the last step in equation number 18a. In writing equation number 18a, we have dropped the constant phase factor and the quadratic phase term was introduced. Okay, so you see that here in writing the second step in equation number 18, we have dropped the constant factor, which is e to the power iota kf, and the rest of the quantities in step number 2 have been set up as O2 prime on the left, as shown on the left hand side of this equation. The Fourier transform of O2 at the zeta and eta plane will be filtered through the amplitude transmittance of the frequency filter, and the filter transmittance, that is Ta prime as a function of fx comma fy, is thus given by the following equation. So let me briefly explain. We have placed the frequency filter over here in this plane, that is at the Fourier transform plane, then which was generated using the object O. Now this frequency plane was incident with the Fourier transform of the object O2. So the filtering will take place of the projected Fourier transform of the object 2 through the frequency plane, and then you know that the image we can see the effect on the image plane. So let's write the amplitude transmittance of the filtering. Let me read this paragraph again. The Fourier of O2 as a function of zeta and eta will be filtered through the amplitude transmittance of the frequency filter and the filtered transmittance. So you see that we are using a word filtered transmittance, which is Ta prime as a function of x and y, is thus given by the following equation. So the filtered transmittance, which is Ta prime as a function of x and y, is equal to the Fourier transform of O2 which we have projected on the TA. What is the TA? TA is the amplitude transmittance of the Fourier transform hologram that we are using. So we are projecting this Fourier transform of O2 in the second step of equation number 18, the Fourier transform of 2 multiplied by the TA, which is the amplitude transmittance of the frequency filter that we have placed, or the Fourier transform hologram, or the Wanderloo hologram, or the Wanderloo filter that we have placed in this setup. So now substituting the values of O2 which we have done, that is 1 over lambda f multiplied by O2 prime as a function of x and y. That is, this is what we have placed the value of the O2, Fourier transform O2 over here, and then again multiplied by TA as a function of xy. And then you know that we are multiplying O2 prime. We have written O2 prime over here as a function of x and y, and then we have written the amplitude transmittance of TA, which is given in the whole parenthesis over here in the fourth step of equation number 18b. And then in the final step of equation number 18b, we have written that this TA, that is this TA prime as a function of x and y, is proportional to this quantity. We are not saying that it is exactly equal, but we are saying that it is proportional to the last step of equation number 18b. So you can see that it is very simple to write that we have multiplied O2 prime, and O2 prime can be seen inside this bracket. Okay, in figure on slide number 17, L3 is the second Fourier transform, is the second Fourier transforming lens which takes the Fourier transform of this TA prime as a function of x and y, which is given below. So you see that in this, look at this one, this setup which takes the Fourier transform again of this quantity, that is the amplitude transmittance TA prime that we have written in equation number 18b. So L4 will take the Fourier transform of that quantity, and then you see that we can obtain the image over here. So let me show this one. So you see that the image at the image plane which we have taken as UIMG, that is the amplitude image at the image plane is equal to the inverse Fourier transform of this quantity, that is TA prime as a function of fx comma fy. So you see that we have used the inverse Fourier transform operator before the curly bracket on the right hand side, and we have plugged in the value of TA prime over here from equation number 18b. And then you know that we have sent this inverse operator, Fourier operator, at each of the term in equation in the second step, and then we have obtained the third step or the last step over here. So the inverse, you can notice the position of the inverse operator operating on O2 prime in the first term, then operating on the O2 mod square of O prime and multiplied by O2 prime in the curly brackets, and then inverse Fourier operator is operating on the curly bracket in the third term, which includes e to the power minus iota 2 pi f sine of theta into y, and multiplied by the two more terms, that is O prime conjugate and O2 prime. And then in the fourth step we have the Fourier inverse operator operating on e to the power iota 2 pi f sine of theta fy, and then two terms with that one, that is O prime and O2 prime. So you see that then we have write down the Fourier transform of each term. The Fourier transform of these exponential terms will be given by the delta functions. So we have, you know, that the Fourier transforms of the delta functions where we have that is the exponentials will be represented by the Fourier transform in terms of delta functions. So let me show the Fourier transform, that is the Fourier transform of that is the inverse Fourier transform of each of these terms in equation number 19. So the amplitude image is equal to A naught into O2 as a function of U and V. So you see that O2 prime over here, which is the spectrum of O2. We have represented it O2 as a function of U and V. And then you know that we are using UV as the coordinates at the image plane, and then you know that we have this term look at this term, you see that the second term over here, these two terms, that is a mod square of O prime, that is the absolute square of O, that is the absolute square of O prime, and then O2 prime are multiplying, so they will convolve with each other, which we have shown over here. And then you know that we have shown the convolution sign over here. So the first one, so the we have shown the convolution, that is absolute square of O2 has been represented by as O as a function of u, we convolved with O conjugate as a function of minus u comma minus v, and then the convolution with that with this term, that is O2 prime in the within the curly bracket, in the second term, that is O2 prime has been represented by a spectrum which is O2 as a function of n as a function of u comma v. And you know that u comma v are the coordinates at the image plane. And similarly, we have written for the third term. The third term involves three terms: e to the power minus iota, that is the exponent terms, then O prime conjugate terms, then O2 prime. So it means that we have three convolution terms over here. So the first convolution term, that is the exponential, will be replaced by the delta function, which is delta of u comma v minus f sine of theta. The second term over here, O prime modulate, O prime conjugate, will be replaced by O conjugate within the parenthesis. We have minus u plus a comma minus v plus b. And then you know that we have the third term, which is O2 prime, and O2 prime, the convolution of the O2 prime is represented by, because O2 prime is actually the Fourier transform, is actually the spectrum of 2 to O2, so we have represented it by the spectrum of O2 at the frequency domain, which is u and v. And similarly, the fourth term has been explained as a last term in equation number 19. So these terms are straightforwardly written, and I hope that if you have gone through the previous, all my previous slides, it is very simple to understand each of these terms, where u comma v are the coordinates at the image plane, and capital U with the subscript imj as a function of u, and v is the field at the image plane. And this cross within the circle we have a cross, this stands for the convolution operator. The following relationships have been used in the derivation in equation number 19. So let me explain. So equation number 20, that is we have absolute square of O prime, which we have represented O prime multiplied by O prime conjugate, and then we have replaced the values of O prime and O prime conjugate in terms of their original spectrals, because we have used the substitutions O prime and O prime conjugate, which we have represented by their actual spectrum. And then you know that we have obtained the last step in equation number 20, that O prime, that the absolute square of O prime has been represented by as the product of O and O prime, O conjugate, or you can simply say that it is the absolute square of O, as given in equation number, last step in equation number 20. And similarly, we have represented the inverse Fourier transform of O prime, which we have represented as the inverse operator operating on, you see that its substitution, which is O as a function of fx comma fy multiplied by e to the power minus iota 2 pi, within the parenthesis we have fx into a plus fy into b plus 1 over 4. And then you know that we have used the operator, inverse operator on this one, and we have obtained these terms over here. So these are also self-explanatory, because you know that we have we have the operator, you know that this is the Fourier operator with the multiplication of the phase term over here, which would correspond to the shifted, which will correspond to the shifted image. And the shifted image is O. Within the parentheses we have u minus a comma v minus b, that we have used the shifting theorem over here. So this is equation number 21 that we have explained. So in equation number 22, we have taken the inverse Fourier transform of O prime, the conjugate of O prime, and we have substituted their values over here. And then you know that we have again used the inverse Fourier operator on this one, because this is the conjugate, this is the shifted conjugate, or this is the shifted spectrum of the object O. And that's why we have the shift. And then you know that we have replaced it with an object which is shifted in coordinates according to the phase shift factor which appears in the inverse Fourier transform operator. And we have applied the shift theorem again to the first step, and we have obtained the second step in equation number 22. And for the equation number 23, we have written the inverse Fourier transform operating on O2 prime as a function of x and y, and that we have replaced simply by the Fourier object O at the coordinates u and v. So you see that we have made these substitutions, that we have used equation 20, 21, 22 and 23 in order to obtain equation number 19. The first two terms in equation number 19 propagate along the optic axis. Look at the first two terms in equation number 19. That is this term and this term. So these two terms. The first two terms in equation number 19 propagate along the optic axis. The third term, which contains delta of u, comma v minus sine of theta, will be focused at the image plane at the coordinate u is equal to 0 and v is equal to f sine of theta. So look at the object coordinates due to this delta function. The object coordinates at which that beam will be concentrated, or that beam will be aimed at this coordinate, that is u is equal to 0 and v is equal to f sine of theta, and is the cross correlation term. The integral representation of this term is given below. So we are writing the third term over here. You know that in the third term we have written all the three terms convolving with each other from the third term. And then you know that we have done the convolution over here. You know that in the convolution this delta will convolve with one of these terms. So we have convolved it with O, with the conjugate of O. That is, we have replaced each u with the u of the delta functions. So u with the we have replaced u in the second term with the u and v of the terms from the delta functions, and that's why we have written the second step, which has a conjugate of o, and within the parentheses we have a minus u plus a minus comma, and then we have a minus v plus f sine of theta plus b, and then this will convolve with the object O2 at the uv coordinates. And you know that this convolution can be represented in terms of the integrals. So we have the double integrals, and then we have the object O over here with the coordinates zeta minus within the parentheses you have a minus u plus a. We have placed a bar over here so that we can, because we have a negative sign outside that one, and then we have another term comma eta minus, again we have used a bar with the terms within the parentheses. We have a minus v plus f sine of theta plus b, because there is a negative sign, and we have placed a bar over here in order to show that we have used these terms as such from the second term. And then you know that we have O2, which is O2 as the coordinate of zeta and eta, and then we have integration with respect to zeta and eta. So you see that this is the definition that the second step is actually the symbolic representation, and you know that the actual representation is given by the last step of equation number 24. So similarly, the fourth term, which contains again a delta function, will be focused at the image plane at the coordinates. So look at u is equal to 0 and v is equal to minus f sine of theta. So this beam will be focused, that is the fourth term will be focused at these coordinates, and is the convolution term. The integral representation of this term is given by, so the first two terms which do not involve delta function, they will be travel along the optical axis, and then these two terms, that is the third term and the fourth term, will be focused at respective coordinates u is equal to 0, v is equal to f sine of theta, and u is equal to 0 and v is equal to minus f sine theta respectively. So we have shown the fourth term over here. So similarly, we shall explain the fourth term over here, that is we shall replace the coordinate in the second term, that is the coordinates within the object. U will be replaced by u of delta function and v will be replaced by v of delta function. And then we have obtained the second term, that is O convolved with O2. And then you see that we have written the third term in the integral form, that is so the second term was the symbolic representation, and the third term, that in equation number 25, that is the last term, is the actual term where we have used the convolution integral in order to represent the second step in equations 25. So we have written equation number 24 and equation number 25. So these are the terms which are not focusing which are not traveling along the optic axis, but they are traveling at an angle to the optical axis, and the angle these beams have centers at u is equal to 0 and v is equal to f sine of theta. You see that we look at the v, we don't have v is equal to 0, but v is equal to f sine of theta. And similarly the fourth term will be focused at u, or the center of the fourth term will be aimed at u is equal to 0 and v is equal to minus f sine of theta. So we have obtained equation number 24 and 25. So out of these four terms in equation number 19, two terms will be symmetrically moving away from the center of the optic axis, but whereas the rest of the two terms are focusing at the are traveling at the along the optical axis. The third and the fourth terms can be made completely unoverlapped. So you see that we have four terms. Two terms are traveling along the optic axis, whereas the third and fourth term are symmetrically at different angles with respect to each other. But you know that there could be an overlap between the third term and the central terms and of course the fourth term. So the third term and the fourth term which are moving away from the optical axis, the two beams which are traveling along the optical axis, that beam may overlap, and our objective is to separate out the third term and the fourth term from being overlapped by the two terms traveling along the optical axis. So let's read this paragraph. The third and the fourth terms can be made completely unoverlapped. The separation between them is controlled by the parameters. Which are the parameters? Let's look at number A, the focal length of the Fourier transforming lens L2. Because you know that the focal length is appearing over here. Look at the coordinates, v is equal to minus f sine of theta. So f appears over here. So A, the focal length of the Fourier transforming lens L2 is a parameter that can be used to separate out the third term from the third term and the fourth term from being overlapped by the two terms which are traveling along the optical axis. The part B is the angle theta the reference plane wave fronts make at the Fourier plane. So you can set the value of angle theta and you can make the position of the third term and the fourth term to be located away from the center of the optical axis. The signals due to the third and the fourth term are located at equidistance from the center, where the signals due to the first and the second term impinge on the image plane. For a given f, the separation of the third and the fourth terms form the first and the second terms can be increased by increasing the angle theta. The minimum angle theta that can ensure no overlap can be found from the signal width shown in the figure. Let's designate W1 and W2 as the widths of the signals O and O2. That is the image of O at the image plane, and O2 U and O2 at the UV coordinates at the image plane. So we are assuming that the signals O and O2 have respectively the widths W1 and W2 at the image plane. So actually this is the figure that we shall be using over here. But let me read first something over. So let's first read this one. Width of the signal in the first term, that is O, as a function of x and y. Its width is W1. The width of the signal in the first term, O2. So O2 is also, you know, that traveling along the optical axis. So O2, which is O2 as a function of x and y, that has a width W2. So width of the second term. So now look at the second term. Width of the second term, this is the second term, you know, and its width is W1 plus W2 because it involves O and O2. And similarly, the width of the fourth term is this one. This is the fourth term. Again, it involves two terms, O and O2. So the maximum width would be W1 plus W2. So we have the total width, the width of the second term that we have written over here. is 2W1 plus W2, and the width of the third term we have written W1 plus W2. The width of the fourth term we have written W1 plus W2. So let me re-explain the widths. You see that the first term is O2, and the width of the O2 we have designated as W2. The width of the second spectrum, you see that the second term convolves cross correlation. You know that we have O convolved with O conjugate. So these two terms are called cross correlation terms because we can convert into the correlation terms. So this is we should not say it convolution term, but we can say that this term, that is the second term, is the cross correlation term, where we have O convolved with O conjugate and then convolved with O2. So the width of O is W. So when it convolved with O conjugate, the width becomes 2W1, that is twice of W1, and it is convolved with O2, the width becomes 2W1 plus W2. So this is the width of the second term. Now in the third term we have these two terms, that is the term O2, is traveling along the optical axis. The width of the second term, which is this one, is also traveling along the optical axis. So this is not the cause, it is also traveling along the optical axis. Now look at the width of the third term. The third term contains delta, then convolved with O star, and then convolved with O2. So delta will not change the, that the width will remain the same. So the width is due to O conjugate in the third term, convolved with O2, and then you know that the width of O conjugate is W1, the width of O2 is W2, so the total width will be W1 plus W2. So the width of the fourth term, the fourth term also involves delta function, convolved with O and then convolved with O2. And you know that delta will not change the width. So we have O, the width of O is W1, the width of O2 is W2, so the total width is W1 and W2. Look at the fourth term and the third term, compare them. In the third term we have O star, that is a complex conjugate of O, and in the fourth term we have just O. So the third term may be called as cross correlation term, because here we are doing the convolution between the term and its between O2 and its and the complex conjugate of O2 and the complex conjugate of O. So this term is called the cross correlation term, whereas the fourth term, which is O2 term, convolved with O. So these two terms don't involve any kind of conjugation. So this term will be referred to as the convolution term. So the third term may be referred to as cross correlation term, and the fourth term is as the convolution term. And you know that we have shown widths of this one. So let me show through the diagram. You know that we have V as the this is the V axis, vertical along the vertical side, and we have the horizontal axis, which will be the U axis, and this is what we have shown. V is equal to 0 over here, and you know that the cross correlation term, which was the third term, is located at a distance f is equal to sine of theta along the vertical axis, and the fourth term, which was the convolution term, is located at a distance v is equal to minus f sine of theta. So this is the convolution term. It doesn't involve any conjugation, where you know that the cross correlation terms involve, which was the third term, involves conjugation of object O. And now look at the central, the two beams which are contributing at v is equal to 0, which that is they are traveling along the optical axis. One term was O2, and you know that O2 has a width which is W2. I have shown the W2 over here. And the second term over here, look at the second term. The second term has a width 2W1 plus W2. So this is the second term that we have shown, 2W1 plus W2. This is the second term. So this is the first term. Both terms are along the optical axis. They will not travel, but they will overlap. So W2 from the first term and 2W1 plus W2 from the second term. These two terms will overlap together. So the overall width of the central area is 2W1 plus W2. Now look at the third term, that is the cross term. The cross term, you see that we have calculated the width of the third term and the fourth term, both are W1 plus W2. So we have shown the cross correlation term, that is the third term, as W1 and W2, the width we have shown, and similarly we have shown the width of the convolution term, which is W1 plus W2, which was the fourth term. And here in the diagram we have shown them separated from the central region. And for that we need some conditions, From the figure it follows that the separation of the third and the fourth terms from the first and the second term can be guaranteed if the following condition is satisfied. That is f sine of theta. Look at that the separation parameter is f sine of theta. So the cross correlation term is separated by f sine of theta. The convolution term is also replicated in magnitude by the distance f sine of theta, or symbolically by minus f sine of theta. So you see that what are the condition? The condition is that f sine of theta should be greater than half the value of 2W1 plus W2 plus half the value of W1 plus W2. So half value of this quantity and of course half value of this quantity. So the separation of f sine of theta should be greater than that one. That is half from the central region and half from each of the cross correlation term or the convolution term. So you see that if f sine of theta is greater than the half values of these widths, then you know that this becomes a total of 3 by 2 W1 plus W2 as given in equation number 26. Or in terms of angle theta, that is theta is equal to sine inverse of this 3 by 2 W1 over f plus W2 over f as given in equation number 27. So the angle that we set for the reference beam should follow this angle, so that the two beams should be just separated from each other. If we know the separations of the angular spectrum, if we know the separations of the terms that we have shown. That is the separation of the W1, that is the separation of the object O, and W2 is the separation related with the object O2. So here you see that we have also shown in the diagram, that is f sine of theta must satisfy the conditions we have shown in equation number 26, and the angle that the reference beam makes during the formation of the van der Rohe filter must satisfy the condition of angle theta given by equation number 27. Width of the signals due to the first, second, third and fourth terms in equation number 19, and the separation of the cross correlation and the convolution terms from the first and the second terms. So you see that we want these terms to be separated from each other, because when they are separated we can filter out, we can see the cross correlation image and the image due to the formation of the convolution terms. So we can see the two images together, that is the image related with the cross correlation term and the image related with the convolution term can be seen separately when they are separated from each other from the central, that is when they are separated from the central region. However, in the central region the two terms will overlap with each other, they cannot be separated from each other. The van der Rohe filter was based on the signal O at the plane zeta and eta, which was applied to the signal O2 again at the object plane. In the filter, the Fourier transform of this was recorded. O may be considered as the required impulse response with the required frequency plane filter as the required coherent transfer function. The properties of the required transfer function for filtering purposes are thus controlled in the spatial domain by the signal O. Convolution filters. Conventional filters for coherent processor cannot be controlled from the spatial domain and are relatively difficult to realize. The recorded van der Rohe filter on the photographic plate or the photoglass can be immersed in a liquid gate if illumination of relative phase shifts is desirable during its use. So you see that here we have explained in this lecture that how the van der Rohe filters can be constructed. We have explained the parameters and the properties associated with the van der Rohe filter. We have explained the mathematics that is associated with that one, and we have explained the amplitude transmittance of the van der Rohe filter. We have explained how the van der Rohe filter can be explained in order to see the filtering effect on another object O2 when it was placed in any of the three optical processors. And we have also explained the extension of these optical processors with the use of another optical system like this one, where we place the Fourier, where we place the filter at the Fourier plane, and then you know that we also project the Fourier plane, the Fourier spectrum of another object which was O2 in our case on this Fourier plane. So we try to compare the Fouriers over here, and then you know that we at the image plane we get 4 terms. 2 of the terms were overlapping each other, and the cross correlation term and the convolution term can be separated from each other. So the images corresponding to these 2 terms can be seen over here. This is what we have explained in this paragraph. So this is the end of slide number 65.